Good morning, everyone. I hope you had one of those nice, strong double espresso this morning in order to follow my lecture that is entitled UHPFRC Upcycling of Bridges and Buildings of High Cultural Value. So it's my pleasure to present you some of our works using a novel type of building material. Table of content. First of all, I would like to show you what is actually behind the acronym UHPFRC. And then the second part, the main part, is actually how we can use UHPFRC in order to improve. And by improvement, I mean rehabilitate and strengthen existing structures, in particular those that have high cultural values. And I will demonstrate the application of this novel technology for structures of high cultural value. What is UHPFRC? You can see here on this photograph, which is a cut through UHPFRC, that actually we have dark areas and white areas. Dark is the cementitious matrix. You can imagine that there is a significant amount of cement and other fine particles, maximum particle size of 1 millimeter only. It's a bit like ceramics. So this is the cementitious matrix, and the white dots are steel fibers. Steel fibers that are very thin, like needles, 0.2 millimeters thin and about 15 millimeters long. And we have a huge amount of those steel needles in this cementitious matrix. This is UHPFRC. And UHPFRC stands for ultra high performance, fiber reinforced cementitious composite. It's a composite material. You might have heard the name also of UHPC, which I think is not the precise abbreviation of this type of material. So UHPFRC is actually very compact, and one of the main properties is actually that it is impermeable with respect to ingress of water, ingress of chloride ions. On the photograph on the left, you see in the bottom part, good old concrete, which has, of course, several problems related to durability. We know all these problems, and we need to fix actually the problems of reinforced concrete by using a much better material, which is UHPFRC. Please, don't see UHPFRC as a concrete. It is not the concrete, because when you say concrete, you will think concrete. And this is just the beginning of mistakes that will be done if these new type of material, I mean, it's quite obvious on this photograph, it's completely different already when you see it. So UHPFRC is not the concrete, it is a cementitious composite. Actually, the best combination of steel and cement. It has been invented already 50 years ago by Hans Henrik Bache in Denmark, and he himself called the material also a compact reinforced composite, or compact cementitious fiber reinforced composite. Never concrete, it's a composite. Okay, that's already a very important first point that you have to keep back and understand. Now let's look at the performance of so-called tensile strain hardening UHPFRC. As already mentioned, we have a very compact matrix. The powders and small particles are actually optimized such that all space is occupied by particles. In this way, we get the very compact and dense material. it is impermeable for water. Water cannot go inside it, in the material. And also chloride ions cannot go inside the material. And this is a main reason why this material can be, or is actually, very durable. As already mentioned, we have a very high amount, more than 3 volume% of steel fibers, short steel fibers in this material. 3 volume%, this corresponds to 250 kilograms per cubic meter of this material. That's a very high reinforcement content compared to reinforced concrete. Now, we need strain hardening behavior. When you see here on tensile stress strain diagram of UHPFRC, we can identify the elastic behavior, and then we have this so-called strain hardening behavior. And all of you'll know this strain hardening behavior actually from steel. So the material UHPFRC behaves much more like steel under tension. However, the values are, of course, relatively moderate compared to steel. But nevertheless, we have a tensile strength of about 12, 14 megapascal, which is a relatively high value once you start designing with this material. The compressive strength of UHPFRC is around 150 megapascal, which is almost as high as the compressive strength of basic steel. Modulus of elasticity is not much higher than the modulus of elasticity of good concrete, around 45 to 50 gigapascal. So these are the most important design values that you need in order to apply and use UHPFRC for structural application. You can actually assume that the material, once you use it, as I will show in a minute, that the material can provide a watertight and crack-free UHPFRC layer for structures under service conditions, everyday conditions. Now, usually UHPFRC is improved, is enhanced actually by adding here reinforcement bars. It is very economic to complement UHPFRC with steel rebars. Or here on the right-hand side, you have actually a fatigue fracture surface, which means that we also studied the behavior on the fatigue of this material, including rebars. Now, the material R UHPFRC is relating to the presence of rebars. And mechanically, we actually add the response of the reinforcement bars, which is schematically this line, to the response of UHPFRC. And UHPFRC has deformation at maximum stress, tensile stress, which is around the same deformation once the reinforcement bar is entering into yielding, which is at around 2.5 per mil of strain. Now, let's look at a very different property of UHPFRC. We should care about carbon emission in construction. And of course, UHPFRC, which is essentially cement and steel, has a rather high CO2 emission equivalent, which is 0.7 kilograms here of CO2. And compared to concrete is significantly higher, of course, but lower than pure steel. It is about 4 times higher than reinforced concrete. So this says already that once we work with UHPFRC, we should use about 4 times less UHPFRC than reinforced concrete if we want to have a same carbon emission amount for a same structural purpose. So this is just an indication. I will come back to the carbon emission and environmental impact of UHPFRC later. So it means that actually, like steel, UHPFRC is a high performance material. We should use as little as possible. We like this material very much, but please use as little as possible. So that's completely opposite to concrete. Concrete is a massive material, and we actually use much too much of concrete because it's so cheap. It's too cheap concrete. Okay. Now in Switzerland, it is for more than 20 years that we apply UHPFRC in structural applications, and I recently established this drawing to give an overview. We had a pilot phase with single applications here. I was involved in all these applications here, and then about 10 years after the first application, there came the consolidation phase with rather with many applications. We introduced standards and so on, and nowadays it is a standard construction method in Switzerland. There are more than 500 applications to my knowledge. So this is a technology that is used in Switzerland, and we are probably #1 in the world in terms of application with respect to the size of the country. Now let's go to the main part. After having introduced this UHPFRC material, we can improve, or we should improve, existing reinforced concrete structures. As already mentioned, reinforced concrete structures are not durable. We have everywhere those durability problems with reinforced concrete, and we need to fix that. We cannot just replace reinforced concrete. It's too big to fail. So we need a new material that can help and rescue reinforced concrete. And this is what is actually outlined here on this drawing. That's the basic concept. We should use UHPFRC at zones that are most severely exposed to water, de-icing salts, that means chloride ions, here in the splashing zone of a bridge pier and so on. The rest is not so exposed to environmental impact, so it can remain in good old reinforced concrete. However, the deck slab is also very much under stress due to loads, and here also we need to help with UHPFRC, as we can see. So the objective is actually to increase the structural capacity of such composite elements and also to provide a protective watertight layer. Now let me quickly jump to the sustainability issue. Actually, sustainability is really preserving the existing structure by using as little amount of UHPFRC. I will come back to this statement with numbers later on. Now, we have understood that the concept is to improve reinforced concrete by adding a layer of RUHPFRC as an additional reinforcement to the reinforced concrete section. So we have such composite elements. And then, of course, the basic question is, how can we get here composite action? What happens at the interface? Now, it is very important that we need to prepare the reinforced concrete substrate by water jetting is the very best method. And it's important to have a wet, moist concrete substrate surface when the fresh UHPFRC is cast on top of it. And if we fulfill these very important and basic requirements, then we can perform tests, we can perform pull-off tests, and these tests will show that the interface tensile strength here along is stronger than the concrete tensile strength. In other words, when we pull on this composite system, it's always the substrate concrete that is the weakest link, the substrate concrete that will fail. So that's the quality assurance criterion. Now the trick with the concept is actually to fulfill several functions with just one layer of our UHPFRC. As already mentioned, increased resistance in bending and shear, increased stiffness of structural elements in order to reduce fatigue stresses, and then of course it should act as a waterproofing layer. The more functions we can fulfill with one layer of UHPFRC, the more economic is the technology. And usually the technology is very economic, which is of course the reason why we have so many applications already in Switzerland. Now this is an overview. The very first application in 2004 on a very small bridge of 10 meter span, but it's a bridge, an important bridge on a very busy road. So here it was like a handcraftsmanship to cast the fresh UHPFRC, small amount, and then 10 years later was really the breakthrough when we casted UHPFRC or our UHPFRC on top of a 2.1 kilometer long highway viaduct, the Chillon viaducts that I will explain in a minute. So there is, of course, lots of development to come from a small application to a large-scale industrial automated application. Now, yes, more than 500 applications in Switzerland since 2004. Why? Of course, the reason is very simple. UHPFRC technology is cost-effective. It must be cheaper and is cheaper than so-called traditional, if not to say old-fashioned methods that are unfortunately still used in this domain. Now let's look at the cost level. UHPFRC material cost is about €1 per kilogram in Switzerland. Swiss prices must be cheaper in other countries. Then the construction cost is actually the determinant level, because this is what the bridge owner or structures owner is paying to the contractor. And I will come back here with numbers. And of course, we can also have side effects by using this technology. We have, in addition to the construction cost, usually the indirect user costs, because interrupting the use of a viaduct is, of course, economic cost for the users. And since we can reduce significantly the duration of works, the indirect user costs are much lower. This is an added value for the owner and society. And on the fourth level, life cycle cost, we can reduce maintenance and the environmental impact, as I will show in a minute. So I really want to stress on this. When you work on UHPFRC projects, the very first question is always costs. Look at the costs. Controlling the costs is an important project quality control. If you come up with a project that is more expensive than what is obtained from traditional projects, then you have a bad design. A design that is not effective, a design that is not using the properties of UHPFRC. Now let's look at the durability. This very first application from 2004 is actually a case where we look at the long-term behavior. And we have now more than 20 years of observations. And when you look here at this photo from 2004, the underside of this short bridge showed actually rebar corrosion. And intentionally, we did not repair this underside. We wanted to observe whether there is ongoing deterioration of this underside in reinforced concrete. Now, when we look at 2014, it's maybe not so easy to see on this photograph, and we have many other photographs, the last ones taken in 2024. Nothing is advancing here in corrosion of these rebars. So this means that actually the UHPFRC layer on top of this slab is really acting as a waterproof layer. It is functional. Then we also removed here in 2014 and in 2024 specimens, UHPFRC specimens, and we were measuring the chloride ingress, because we have here a road and in wintertime they are spreading de-icing salts on this bridge. And actually we almost didn't find chloride ions in the UHPFRC, only in the very first 2 millimeters depth and very little amount. Then the pull-off resistance was larger than 1.5 megapascal, and the fracture occurred in the substrate concrete, which means that actually the bond between UHPFRC and the concrete substrate is intact. So until today, there is absolutely no sign of any damaging process, which is a kind of validation when I'm stressing on the fact that UHPFRC is really durable. Now let's come to the Chillon viaduct, which is a 2.1 kilometer long highway viaduct. This is really a major structure. Very nice design, very innovative, and without going into detail, after some years of use, we had to state that there is actually, in addition to the usual rebar corrosion problem, we have in the concrete here alkali aggregate reaction, which of course is progressing once there is water going inside the concrete. So the problem was actually that the slab that they designed at that time in the 1960s is rather thin, and we had to design an intervention. Actually, initially, the engineers designed using, let's say, so-called traditional methods to strengthen this viaduct, but then they found out it's very expensive, and they came and were asking whether UHPFRC is a method, and together we developed this concept, which is very simple. So we have a layer of R UHPFRC of 50 millimeter thickness on top of the existing reinforced or post-tension concrete slab here. And to fulfill several functions, increase the resistance of the deck slab in the transverse direction, and then also in the longitudinal direction, this thin layer of UHPFRC increases the structural stiffness and resistance of the girder, the haunch, the box girder, by about 20%. And then, of course, it's the waterproofing layer. And very important is that we did not increase the self-weight, because once you increase the self-weight by using, for example, old-fashioned methods, then, of course, you have to strengthen the box, you have to strengthen the piers, and then it becomes really expensive. Also, this is a busy highway, so the intervention needs to be very short. So these were the functions that we fulfilled, and it was realized, as already mentioned, here in summer 2014 on the first viaduct. significant amount of UHPFRC, and the intervention cost was at that time 240 euro per square meter. And these are Swiss prices. And this price includes the concrete surface preparation. To fulfill all the functions that I mentioned, this is a very cheap price. Now, how has this been done? UHPFRC ready-mix plant was put on site by the company here. So it was all automatic here, controlled by a computer, 2 mixers, automatic mixers, and so on. Here are the fibers that are delivered into the mixer. And this is the fresh UHPFRC coming out of the ready-mix plant, to be transported to the site, casting site, where a machine has been used, like a paving machine, in order to cast the fresh UHPFRC with a thickness of exactly 50 millimeters. There is not 1 millimeter more or 1 millimeter less. We can be very precise. It's high tech. You see here also the rebars, of course, that are arranged in both directions within this 50 millimeters thickness. Here you see some photographs of what comes out behind the paving machine here. Of course, there need to be some some working joint detail. Especially, we had a slopes of 7%. The material needs to hold slopes, but all this can be solved. Now, I would like to explain also that actually this is a heritage structure. It is one of the most important and, in my eyes, most beautiful highway viaducts in Switzerland. It is just above the most visited monument in Switzerland, which is the Chillon Castle. So actually on this photograph, we have 2 monuments of national value. And of course, it's very important that we do not disfigure such a slender and nice highway viaduct by using old-fashioned methods. And we can do with the UHPFRC method, we actually preserve the aesthetics of the highway viaduct. Okay, let me come to a next application, which is the Valchiel Bridge, designed by Robert Maillard. I think you know more or less the works of Robert Maillard, who was a pioneer in reinforced concrete in Switzerland. Very slender structures. And in this case, that was back in September 2013, we applied here also on the bridge deck a layer of UHPFRC and some pea gravel in order to obtain a layer of UHPFRC where you can drive and walk on it directly. And of course, it is also the waterproofing layer. It increases the stiffness of the deck slab. So that's, of course, also a monument, an important monument in bridge engineering in Switzerland. Another small bridge that we really rescued from demolition here is this road bridge. It's a small road bridge in a remote area from 1934. And here we applied also a layer of UHPFRC, RUHPFRC, in order to strengthen and waterproof the deck slab. It is actually a structure. It looks like a concrete beam, very slender beam. And how is it possible to make it such slender structure? Actually, it is a beam that has been built according to the Milan system. So you build first a steel structure and you cast around concrete in order to obtain like a reinforced concrete slender beam. So this is what we preserved in the end as a monument by using really this very smart and non-invasive UHPFRC technology. Now let me come to a much larger viaduct, a railway viaduct, which is 800 meters long. And in this case, we did first some monitoring-based fatigue safety verification. So all those who know a little bit railway bridges, they know that usually the railway authorities, they just throw away riveted steel structures from the 19th century. So this viaduct was built in 1896. And of course, there is an issue about fatigue safety. And what we did is actually not just calculating this riveted structure, but measuring the stresses here, the heartbeat, when the train is running over the riveted structure. And by doing this, which is also in itself a novel type of engineering method, we could show that there is absolutely no fatigue issue with this riveted steel girder. Now we had to build a new track on top of this riveted girder, a new trough, and the design idea was to use a lightweight material, a lightweight structure, because once you use, for example, reinforced concrete, which would be what I call the old-fashioned method, then of course you add such a huge amount of dead weight that you cannot keep the lightweight riveted steel structure with it. So we designed a lightweight trough in UHPFRC, which looks like this. It is close to the design principle is much closer to steel construction. And so we have very thin plates, 60 millimeter plate here, and stiffeners in bright green in the transverse direction. So this was the rendering in 2018 when I designed this UHPFRC intervention. Some views from the construction in 2024. We see here those precast trough elements in UHPFRC. Of course, there are more massive parts here where we need to connect with the top flange of the riveted steel structure. We also used UHPFRC here in order to have a waterproof and stress-reducing layer inside the trough on top of the natural stone masonry part of the viaduct. So you see here the natural stone part with the very nicely designed original natural stones at the finishing line of this viaduct. This could be preserved. That would be impossible once you design with concrete such an intervention. But with UHPFRC, we end up with a very thin cantilevering slab. So here at the extreme, we increased the thickness to 100 millimeter, but the slab, this cantilevering slab, is only 60 millimeters thin. So let's have some look at this viaduct after the intervention. Pictures from a year ago. Of course, the riveted steel structure was renovated, new corrosion, anti-corrosion painting, and so on. You see here the stiffness in the transverse direction of the UHPFRC slab and the cantilevering slab all over the viaduct. You see here very thin UHPFRC line connecting now all elements of this 800-meter long viaduct. Another application in the domain of, I need to mention that, of course, this is also a monument of a national value in Switzerland, in downtown Zurich. And this also is, of course, a monumental structure, riveted structure, that was in a very bad shape. And it had a slab, a massive reinforced concrete slab in a very bad shape. What can you expect else from reinforced concrete than being in a bad shape? So the idea was actually to remove this rotten, heavy reinforced concrete slab by a lightweight, 4 times lighter R UHPFRC slab. In this way, it was not necessary to strengthen the original riveted structure. There is no additional plate or what else put on this riveted structure, only some repair at places where we had some corrosion damage. And you see here on these pictures the lightweight R UHPFRC elements that were placed on top of this structure. The cost was only 50% of what a new bridge would have costed. Now let's summarize a little bit the bridge part and greenhouse gas emissions up here. So we have the carbon footprint in terms of kilogram of CO2 equivalent per square meter of useful bridge surface. And we were looking at about 15 UHPFRC improvements on reinforced and post-tensioned concrete structures. Here you see the Chillon viaduct, and the carbon footprint was around maximum 200 equivalent kilogram of CO2. And we compared, and in many of these cases, we had actually the demolition replacement project that was, of course, much more expensive, and what was finally not done. And it also represented a certain carbon emission output, which was at the level of 2,400. So we can, in short, say that the traditional engineering practice, which consists in demolition and replacement, some engineers say that structures are at the end of their life and need to be replaced. No, they don't need to be replaced. They can be improved by using the UHPFRC technology. And in addition, we have a reduction of the carbon footprint of 92% in average. 92, that's a huge amount. So it's also from the environmental viewpoint very interesting to use this new technology. Now let's look into a building which is a monument of regional importance in downtown Zurich. A building from 1913 with early reinforced concrete. It's the Hennebig system with thin ribs under a thin slab. And this building was renovated and modified for new use as a hotel now. And there was a need to strengthen the slabs, and the idea that was realized, the concept was to add here 40 millimeters of UHPFRC on top of the existing concrete. Of course, all this had to be designed. Like all bridges that I showed you, there is a significant design work behind it. And we also conducted here, in this case, we had the chance to test the concept on parts that could be removed from the existing building and that we could test in the lab in order to see whether our design really corresponds to the real behavior of the strengthening. Some impressions from the casting here of the UHPFRC, fresh UHPFRC. In this case, only some parts of the slab were strengthened using UHPFRC. Other parts, it was sufficient to use just mortar, which was of higher cost. So it's always good to be very pragmatic in this kind of application. So we increased with UHPFRC, let's say our UHPFRC, we increased the structural resistance, the rigidity, the stiffness of the slab, to reduce vibrations, of course, in use, small increase of static height, and the existing structure was actually preserved, which was a main objective from the viewpoint of cultural values. Here also we calculated the global warming potential of this application, and compared to traditional methods, the reduction was almost 40%. I'm currently working on other heritage building from 1919, and the design is very similar to the previous case, strengthening of ribbed slabs, Hennebick slabs, by our UHPFRC layer. So this will be realized probably next year. Same principle, same concept. I would like to conclude my presentation here. Of course, UHPFRC can be used to design and build new bridges, pedestrian bridges, for example, but we also built road bridges and railway bridges using this type of material. But this I can report on at some other occasion. Let me conclude for today's lecture. Number one, UHPFRC is a new composite material. It is closer to steel, and it's better to think in terms of steel construction. And if you have experience, composite plastic materials, which is a lightweight material. Once again, UHPFRC is a new composite material. Second, we use UHPFRC to improve existing structures, in particular existing reinforced concrete structures. UHPFRC technology is used to preserve heritage structures, because in the case of heritage structures, the technology allows to be non-invasive. You can almost not see the intervention, the strengthening intervention using UHPFRC. And number four, UHPFRC technology enhances also sustainability of existing structures. Actually, the heritage people, for them it is quite obvious what sustainability is. Sustainability is, in one sentence, preserving the existing by adding only little amount of new materials or new technology. Let's be non-invasive. Okay, with this I would like to thank you for your attention, and hopefully this photograph will motivate you. I suspect that you are younger colleagues, and we need younger colleagues to introduce new technologies into our very interesting and fascinating domain of engineering of existing structures. Thank you very much.